Greetings everyone. I am Balaji, Assistant Professor from the Department of Civil Engineering at SRM Madurai College for Engineering and Technology. Today I'll be taking the topic free body diagram from the course Engineering Mechanics. So the introduction to the free body diagram. So what is a free body diagram? In general, a free body diagram is a representation of of an object that is placed on a surface and it represents all the forces acting upon it. So as a simplified definition, we can say a free body diagram is a simplified representation of an object isolated from its surroundings, showing all the external forces acting on it. So it's like removing everything around an object and just focusing on the forces acting on the single object. So consider any object. We can consider any object. Consider this to be a concrete block. It is placed over a surface, a flat surface, and a, of a, for example, someone is pushing from here, another person is pushing from here. So the force with which this person one pushes is W1, and the force with which the second person pushes is W2, and there will be a particular force. There will be a particular weight which is dead mass or dead weight acting from this concrete block, and all these forces are acting on this particular concrete even while it is in rest position. So a free body diagram will represent all these forces. So this force W1, W2, and this dead weight. So free body diagram will be a representation of all these forces in a simplified manner. So the concrete block will be removed and the diagram will be like this. This is a rough representation. So it will consist of all the forces acting on it, on whatever direction it may be, all the forces acting on it. So W1 will be the force acting due to the force applied from person one. W2 will be due to the force acting due to the force applied by the person to the person two, and WD will be the dead weight acting from the concrete block. This is a rough representation of a free body diagram. So, so this particular diagram is a 3D representation, and this particular diagram is a 2D representation or a simplified representation, which is also called the free body diagram. So, for example, if we consider an example, consider a box on a table with forces like W, normal force N, and friction F. So, if we consider this one, we can get a diagram like this. It is placed, you can see it is placed over a wedge or a slanting surface over which a box is placed. You can see the box is placed, and W is the dead weight, which is the mass. For example, dead weight is any weight that doesn't change with uh, what is it with space or time. So consider you as an object. Consider you as an object, and your weight, your body weight, is known as dead weight. So for this box, its own weight is known as dead weight W, and a reaction force is acting upward from the box, which is known as N, which is also known as normal force. So friction, it is sliding from the top, or it is moved from the bottom to the top. So at any direction, frictional force is the force that is acting opposite to the movement of the object. So a reaction force that acts perpendicular to the object, a W, a dead weight, which acts straight down, and a friction force that acts in the opposite direction of the applied force. So you can see F applied force is here, and it is the box is moved upward to in the inclined plane, and the friction force F is in the opposite direction of the box movement. So a simplified representation of this particular diagram would come to be a dead weight, an applied force, and a reaction force. So this particular angle theta will be equal to this angle theta, and here it will be 90 degrees. That is the reason why it is known as normal force. So just opposite to this applied force will be a straight line denoting friction force. So this will be a simplified diagram, simplified representation of the free body diagram for this particular example. Now let's consider the common forces acting in a free body diagram. So in common, all these types of forces will act in a free body diagram. So first one is the weight, or which I denoted as dead weight. So it'll be represented by the formula mass into gravity. So mass is the weight or the thing that is shown on a scale in kilograms, and g is the acceleration due to gravity. So mass is multiplied by the acceleration due to gravity to obtain the weight or the dead weight in Newton. So always the direction of this weight will be downward, as it is directly related to gravity. You can see W is directly related to gravity, so the direction will be downwards. So second one is the frictional force. So frictional force is represented by mu into N. So this always opposes this always play um, this always acts in the direction that is opposite to the motion of the force. So if the box is moved front, the friction force will act backwards. If the object is pulled backwards, the friction force will act forward. So third one is the normal force. So normal force, the formula depends on the context, because the normal force isn't always the same for it depends upon the cross sectional area and the inclination of an object, but the direction of the normal force always will be perpendicular to the surface, whatever may be the surface and whatever be the inclination. When the object is placed at rest, the normal force acts in the direction perpendicular to the surface. The fourth one is the tension. So for tension, the formula is there is no standard formula, but it is solved using equilibrium. So this tension is anything that is applied externally. For example, if the object is tied to a rope and pulled, the tension acts over the rope, or the torque acts over the rope. So the tension depends on the puller, on the force that is applied over the rope. So you can see the direction is always along the rope and away from the object. So the next one is applied force. Applied force is barely pushing the object or pulling the object. So it is given or assumed. Generally it will be given or it will be assumed depending upon the weight of the person pulling or applying the force. So the direction will be to the direction that generally the person gives. So moment this acts upon any hinged or fixed ends. For example, if there is a fixed end to which the rope is tied, the rope where the tied end is placed, there will be a moment acting due to the dead weight of the object. So it is given by the formula F into D, where F is the force and D is the distance between the fixed end and the center of the object. So moment always is either clockwise or anti-clockwise or counterclockwise. So you can see the free body diagram here. It is a block. It is a square or a rectangular block. So F is the applied force. F is the applied force, and you can see the dead weight is equal to m into g, which is the weight of the box, and n is the normal force supporting the mass. It acts upward and 90 degrees, and small f is equal to mu into n, which is the frictional force, where mu is the coefficient of friction, m is mass, g is acceleration due to gravity, which is always assumed as 9.81 meter per second square, and d is the distance between perpendicular distance to the axis of rotation, which is used in the moment. The representation of a free body diagram. For horizontal planes, this 2D static equilibrium, it is assumed that all the forces acting along the horizontal direction is zero, and all the sum of all the forces acting the vertical direction is zero, and sum of all moment is equal to zero at any point. So these three equations are used to solve the given free body diagram. So for inclined plane, consider this diagram. You can see the first diagram, you can see a box is sliding over an inclined surface at an angle theta. So you can see a pulley is placed here and a mass block is placed this side, and it is tied to the box. So this mass moves this block in the upward direction towards the pulley. So considering this diagram, we can see 1, 2, 3, 4. Totally 4 forces acts on this particular in diagram, and this tension and mass are correlated and this denoted as tension only because this tension directly depends upon the mass that is applied. So this tension is nothing but the mass that is applied. So 1, 2, 3. So totally three forces are acting upon this. So if we are resolving this, we can see this theta will be coming here as theta. This theta will come here as theta, and the normal force is placed here, and Wg or the dead weight is placed here, and this particular tension force is resolved into Fg cos theta and Fg sin theta, where cos theta comes for the horizontal component and sin theta comes for the vertical component. You can see this is the simple representation of the free body diagram, and from this free body diagram the given angle theta is resolved into Fg sin theta and Fg cos theta. So this is an important part in a free body diagram. Whenever a force is incident on a surface with an angle theta, it is resolved into a vertical component and an horizontal component. So the vertical component is denoted with cos theta, F into cos theta, and the horizontal component is denoted with sin theta. This is an important this is an important topic in the view of free body diagram. So next we can see an example of a free body diagram. In general, in general, an actual body will be represented as such. It is of dead weight and it is hinged at or it's fixed at both ends A and B, and and the angle with the horizontal surface is theta 1 and theta 2. So a free body diagram may be drawn as such, which is TOA, where it is a tension acting along O to A, and TOB, which is a tension acting along O to B. So this is both the thetas, the angles, and this W is the dead weight of the object. So always tension is represented towards the fixed end or towards the external force applied. So that is the reason it is named as OA and not AO. See, these are the important points we need to note along in the concept of free body diagram. And if there is any doubt, feel free to contact me from the contact details I have given. Thank you.